Over many iterations, the agent learns to make decisions that maximize a desired outcome, whether that means winning a game, navigating a space, or balancing complex variables in an automated system. Reinforcement learning is particularly valuable for scenarios where a sequence of decisions must be made under uncertain conditions. Another area of progress is found in generative modeling. Generative models are capable of producing new data by learning the patterns within existing datasets. For example, once trained, a generative model can produce realistic images, simulate human voices, generate music, or even construct new videos. These models operate by mapping underlying structures in the data and then using those structures to synthesize new, plausible content. This capability is essential for creative tasks, simulation training, and enhancing digital media. In modern digital systems, these technologies extend far beyond individual devices. They are now used to personalize digital experiences by tailoring content based on user behavior, preferences, and past activity. These systems can translate languages in real time, recognize human faces in photographs, and interpret spoken commands. By interpreting and predicting user intent, they improve communication, accessibility, and overall engagement with digital platforms. Large-scale environments such as connected homes also benefit from intelligent systems. In these settings, various sensors and devices gather data from everyday activity. Lights, thermostats, appliances, and security systems can all respond dynamically based on user habits and external conditions. This network of interconnected devices enables homes to operate more efficiently and securely, adapting automatically without the need for manual input. At an even broader level, the integration of artificial intelligence into urban design is giving rise to the concept of the smart city. In such cities, digital systems collect and analyze data from sources such as traffic patterns, energy usage, waste management, and emergency services. Intelligent algorithms process this data in real time to optimize public infrastructure, reduce congestion, improve energy efficiency, and enhance safety. For example, traffic signals might change dynamically based on vehicle flow, or utility systems might adjust water and power distribution based on consumption forecasts. The intelligent core of a smart city processes the data received from countless sources, transforming raw information into actionable insight. This is supported by connected systems that include cameras, sensors, and vehicles. While these components gather environmental input, intelligent decision-making engines interpret the data, offering real-time responses or suggestions. The result is a city that becomes more responsive and adaptive to the needs of its citizens. Underpinning all these advances is a growing ability to manage, analyze, and derive meaning from large volumes of information. Tools for data analysis allow systems to sift through complex datasets and find relevant patterns. These insights are used to improve performance, predict future events, and make more informed decisions. Whether in research, transportation, healthcare, or energy management, these technologies continue to transform the way machines and humans interact. In recent years, a new frontier has emerged in the study of consciousness, intelligence, and synthetic biology through a project that brought together living brain cells and digital systems in a shared environment. Known broadly as the dish brain experiment, this effort involved growing a network of neurons in a carefully maintained dish, then connecting that biological network to an artificial interface. What made this project exceptional was not simply the growth of neurons outside a living organism, but the integration of these cells with a digital platform capable of reading and responding to the neural signals. In doing so, the experiment represented one of the earliest steps toward creating systems that combine biological intelligence with engineered systems. The neural cells used in this project were cultured from human and animal sources and then encouraged to form synaptic connections, just as they would in a natural brain. Over time, these connections developed into a functioning network capable of responding to stimuli. The most astonishing result was that the neurons could be trained to perform a task that involved interacting with a simple digital environment. In this setup, the neural network demonstrated learning behavior, improving its performance in response to feedback, and behaving in a manner that suggested rudimentary awareness of its virtual surroundings. The system used to facilitate this interaction was designed to interpret the electrical activity of the neural cells and translate that activity into signals that affected the environment. When the network responded correctly to input, it received positive reinforcement, and when it made errors, the reinforcement was withheld or altered. This feedback loop, reminiscent of behaviorist learning in animals, led to observable changes in the network's behavior. Over time, the cells appeared to adapt their activity to achieve better outcomes, demonstrating a form of learning that did not rely on traditional software programming but on organic change within the biological material itself. A more recent evolution of this concept came with the development of a more advanced system known as the cortical learning platform. This new setup improved upon earlier designs by enhancing the degree of control, observation, and environmental complexity the neurons could engage with. In this platform, the neural network was exposed to increasingly nuanced stimuli and more complex feedback, allowing researchers to study how biological intelligence scales with complexity. Observers noted that the network could retain information, adjust behavior across sessions, and even generalize from previous encounters, all using its living synapses. What distinguishes these systems from conventional computing is their dynamic plasticity.